Hello guys, how are you doing? This is the problem, or one of the problems that I wanted to reach now, because every time the students see a spring over there, they go like if it's a horror movie with horror night. Oh, springs, no, please. I mean, what is the wrong thing about springs? I see springs, I see forces. That's what you have to do, forces. So first of all, let's start reading as we put some numbers here into this free body diagram that we are constructing. It says 30 kilogram block. Let me put here 30. But if you know, you remember that it's not 30, right? It's 30 kilogram, but we need the force, so I have to multiply that by 9.81 meter per square second, and then you will have something like, let's see, 30 30 times 9.81, 294.3 Newton. Perfect. And now we're gonna have a force acting here and a force acting here that are gonna, those forces provided by the springs are gonna hold that weight into that position shown. This force will be AC, this force will be AB. Now the problem is asking, and you have the stiffness of the springs here. The problem is asking the unstretched length of each spring. So basically, originally, or in this position, we have the springs stretch. This is the stretch length of the springs. And this is something that we're going to need to calculate the stretch length of the spring, and we can do that very easily because we have the geometry here. So this is going to be, for example, this stretch length is going to be just square root of 0.6 squared plus 0.5 squared. Let's do that. Let's call that length, stretch length of a spring AC. That's going to be square root of 0.6 squared plus 0.5 squared. And the stretch length of AB, also given by geometry, is the square root of 0.4 squared times 0.5 squared. How much is this and how much is that? Let's check that out. 0.6 squared plus 0.5 squared elevated to the 0.5 for the square root. That's going to be 0.781 meters. And this one here, the stretch length of AB will be 0.4 squared, 0.5 squared, elevated to the 0.5, which is the same thing as extracting the square root meters. Okay, we have the stretch length. Now, what happened with the springs? You know that you have the force in the spring is equal to K, where K is the constant of the spring, and that constant is also called stiffness of the spring, and basically is if I apply a force, how much is going to, that's a ratio, that's a relation between the force applied and the stretching. Or you can say that is the slope of, if this is stretching and this is force, this is going to be K within the elastic range. This K applies to a lot of metals, also in the elastic range, or all the metals, but then it's called modulus of elasticity. And it's good that you start getting familiar or familiarized with those terms. But that's basically what it is. In other words, if I know the force acting on the spring and I know the constant of the spring, I can calculate the stretching of the spring. And the stretching of the spring will be the force divided by the constant of the spring. In other words, we need to find AC, we need to find AB. How? Particle equilibrium, summation of forces in X, summation of forces in Y. Two unknowns, two equations. Summation of forces in X equals 0. Another thing that I'm going to need are the angles. So let's see this angle alpha and this angle beta, alpha and beta. If I want to calculate alpha, alpha will be the inverse tangent of 0.5 divided by 0.6. And beta will be the inverse tangent of 0.5 divided by 0.4. Sorry. Inverse tangent, 2 times 0.5 divided by 0.6. That's 39.806 degrees. And inverse tangent of 0.5 divided by 0.4 will be 51.34 degrees. Now we have alpha and we have beta. Now we can do summation of forces in the x direction. What do we have in the x direction? We have this component and this component. That's it. What is this component? Oh, this component is going to be AC cosine alpha. So AC cosine of 39.806, and remember, because it goes to the left, I didn't say it before, but I'm assuming this positive, positive. So this will be to the left, which means it will be negative, contrary to what we assume as positive, plus this one. What is this one? AB cosine beta equal, there's nothing else, 0. And now we can do summation of forces in y equals 0. And what do we get in y? Well, we have this component and this component. This component will be the equivalent of this. This component will be the equivalent of that. And the weight. So this component will be what? Will be AC, because it's opposite to alpha, sine alpha. AC sine alpha. But alpha, we said that it was 39.806 plus AB sine beta minus, that will be here, minus 294.3 equals 0. But I'm going to pass this to the other side of the equation, so it's going to be equal to 294.3. Why I did that? Because now I have a system of equations that I can use the calculator to solve. How do you solve that? Once again, you go here, system solver, 2 by 2, and we put these values. First, negative. Negative what? Negative cosine of 39.806, close parentheses. Now we land in this plus here. You see? In that plus over there. Let me check this again. Minus cosine of 39.806, 0.77. Now this is plus. We landed in the plus. We have to move. Either you hit enter, you hit plus, or you move. This is going to be cosine 51.34. That's the value that you get over there. Now this one here will be what? Will be sine 0 equals 0. I'm sorry. 0. Now this will be sine 39.806 plus this one here will be sine 51.34. Oh, you see, I told you to do that and you haven't. Plus, and then I do it. Sine 51.34 and equal to 294.3. 294.3. So, and then we have the results. X is going to be AC, 183.89 Newton, and Y is going to be AB, 226.13 Newton. Now what do we need to do? These are the forces. We have the forces now for each one of the spring. If I need to know the stretching of the spring AC, stretching of AC, it will be what? It will be the force, 183.89 183.89 newtons divided by the constant. Now this constant is in kilonewton. Remember, 1.5 times 10 to the third newton per meter. This and this cancel out, passes to the top. So you have a stretching of the spring AC as 183.89 divided by 1500. 183.89 divided by 1500, and that would be 0.123 meters. And the stretching of the spring AB will be the force of the spring AB to 26.13 newtons divided by the constant 1.2 times 10 to the third newton per meter. 226.13 divided by 1200, 0.188 meters. Now, I have the stretch length of AC and the stretching of AC. What do I have to do? Stretch minus stretching, that will be original. And that original is going to happen when we release this. When we release this weight, the springs are going to come somewhere here. And this is going to be the length that we are looking for. This length. The unstretched length for those springs. How much is that? I don't know. Where is this point? I don't know. We could calculate it, but this is not what we need to do. So a stretching length of AC for AC, then we have 0.781 meters minus 0.123 meters. And for AB, this is unstretched or original length. That will be 0.64 minus 0.188, and the answer will be for both in meters. So this is 0.78 minus 0.123. That will be 0.657 meters, and for AB, 0.64 minus 0.188, and that will be 0.452, 0.64. This 0.64, yes, this 0.188, yeah, this is 0.188, so this is 0.452 meters. So this is what the problem is asking you to do. Now, my advice, get the same problem and flip it. Start the problem by saying the resorts or the springs have an original length of this much, and after hanging this weight, these are the constants, after hanging this weight, then it reaches the configuration shown in the picture. How much was the weight that we hang in there? That's another way of doing this problem. Or you can say calculate the constant if you know the original and the form shape is this one, and get the same problem and flip it in different ways. So whenever a problem like this hits you, you don't have to guess. You really understood the concepts. See you in the next video, guys. Have a good day.